Alright, so I'm going to walk you guys through the examples for limiting reactant problems. So you have this paper from class and you can just follow along with how we solve it. So the question says a mixture of 10 moles of hydrogen and 7 moles of oxygen is reacted to form water according to the following reaction. So we have our reaction, and it's always important to note what our coefficients are in the balanced reaction because we might be able to use those. It says which chemical is a limiting reactant and which is an excess. So we're going to start with that question, well, that part A, and then we'll come back to the rest of it. These questions are a little bit different because you're given, instead of being given one number to solve the equation with, you're given two. So we need to decide which reactant is controlling the reaction and giving us our amount of water, our product. So the approach that I take to this is by starting with the moles of each reactant, so 10 moles of hydrogen and 7 moles of oxygen. And what we want to do, since our question is figuring out how much water is produced in this, and we're trying to see how much water we can make, the first thing I always do is convert both of these to water. So we set up our railroad tracks. We want to go from moles of hydrogen to moles of water. Okay, so we're going to see how many moles of water can actually be formed here. So we're going to use our balanced equation, so 2 moles of hydrogen for 2 moles of water. So it's a 2-to-2 ratio or a 1-to-1 ratio. We can reduce that. And so we can produce 10 moles of water when 10 moles of hydrogen react. Now we're going to do the same setup, same type of thing for oxygen and see how much water can be produced if all of the oxygen reacts. So we take moles of oxygen on the bottom and moles of water on the top. It is a 1-to-2 ratio, 1-to-2. So 7 times 2, we can get 14 moles of water. So what does this tell us? Well, if all of the hydrogen reacts, we can make 10 moles of water, but if all the oxygen reacts, we can make 14 moles of water. Well, since these two amounts are being mixed together, we can only create the smaller amount, because once we make our 10 moles of water from this hydrogen, it's gone, it's run out. So we can't quite get to this 14 moles of water that our oxygen predicts. So we can produce 10 moles of water, because that's the lower amount. So that's going to be our amount of product that's formed. Now, the question for this first part wants to know which is the limiting reactant and which is an excess. So the chemical that runs out or is going to produce the smaller amount of product is our limiting reactant. Now the key here is to always label the reactants, this part here, not what's over here, because if you notice they're the same chemical. So if I label this as limiting and this is excess, that is labeling the same chemical as both, and we can't have that. So you always label the reactants. So limiting reactant. Okay, it's key that it is a reactant, not a product. So that means if hydrogen is our limiting reactant here, then oxygen must be our excess reactant. So through that, we are able to answer this first part, which chemical is limiting and which is an excess. And the second question, let's call this part B, is how many moles of water are formed? Well, we already figured that out. We found out that 10 moles of water are formed or produced in the reaction. So we did part B there. So we've done both of the questions, and we can check the steps here. I do have the steps listed, but basically we can convert each chemical to moles of the product. So we did that here, converted to moles of the product. Compare moles from each conversion. So we compare 10 to 14. The smaller value will determine the limiting reactant. So our smaller value in product determines which reactant was limiting. So we label the given chemicals as limiting and excess and state the number of moles of product formed. So we have done all those. So figuring out our limiting reactant and our excess is not too bad when we're dealing in just moles, but in reality, we cannot measure moles in a laboratory. We cannot measure moles at all. So we're not usually given moles in a proper problem. We're given grams. So let's think about what that would do to this. If we were given grams here instead of moles, we would have to first convert whatever grams were given into moles. Then we can do this same process. So whatever grams were given of each reactant, we convert to moles, and then to moles of the product. So it just extends the question one more step, but it doesn't change this piece. We still have to get to moles of the product. So let's take a look at an example of that. Slide this paper down. Okay. All right. It's going to cut off a little bit, but I want to make sure you guys can see my writing. So the most important commercial process in converting nitrogen from the air into nitrogen-containing compounds is based on the reaction, reaction of nitrogen and hydrogen to form ammonia. So this is one of our most important reactions, and it produces this ammonia, and we use ammonia in fertilizers. So this is probably one of the most important reactions in our lives because we need fertilizers to grow our crops and all that. So it's called the Haber process. Haber, he's one of the people that helped come up with this reaction and make it successful. So it's pretty important. We'll see it a lot this year. All right, so again, we want to check out our coefficients. We've got 1 to 3 to 2 ratio. So we use those in our conversions. So our question says how many moles of ammonia, so we're looking for moles of ammonia, can be formed from 84.06 grams of nitrogen and 24.24 grams of hydrogen. So we're given, again, 2 given numbers instead of just 1. So we need to be able to first decide which substance is going to control the reaction. The limiting reactant is always the one that controls the reaction. So, same steps that we had before. We're going to convert each of the chemicals to moles of the product. So, in this case, our product is ammonia. So, scooching this down a little bit. All right. So, our first chemical, we have 84.06 grams of nitrogen. So like I was saying, this process is not going to change much. We're just going to add one step to it. So first, we can't go directly to our moles of product. We got to get this in the moles first. So grams of nitrogen into moles of nitrogen. We use our periodic table to find our molar mass of nitrogen. So one nitrogen atom is 14.01 grams. So 14.01 plus 14.01 gives us 28.02 grams in 1 mole of nitrogen. So that allows us to go ahead and cancel out our grams of nitrogen, and we can move on to the next part of the conversion. So we want to get to moles of the product. So we want to get rid of moles of nitrogen, and we want moles of our product, which is the ammonia. So from here, this is our mole ratio. We're not changing units, but we are changing chemical, and we refer to our coefficient. So nitrogen's coefficient is 1, and ammonia's coefficient is 2. So now we have been able to get rid of our moles of nitrogen, and we're left with moles of ammonia, our product. So we're going to do some math. My calculator here. So we've got 84.06 times 28, let's see, let's move this up here so you guys can see, 28.02. Oh no, we're going to divide. Divide. And we're gonna get that and multiply it by 2. So we get 6. So we're gonna get 6. Now this is 4 significant figures here, so 6.000 moles of ammonia. Alright, so that gives us one piece, but that's not our final answer. We have to do it for both of our givens because we don't know which one is going to produce less product. So 24.24 grams of hydrogen. Again, we want to get it to those moles of ammonia, so first we have to change this to moles. Grams of hydrogen, moles of hydrogen. So in 1 mole of hydrogen, its molar mass is 1.01, so we times it by 2, 2.02. And we can get rid of our grams of hydrogen. And then change from moles of hydrogen, again, to moles of our product, moles of ammonia. So we want these 2 units here to match each other, these 2 things, so we can compare them. So we look at our balanced reaction, 3 moles of hydrogen to 2 moles of ammonia. And now we're going to do our calculation. So 24.24 times 2 divided by 2.02 divided by 3, 8. 8.000 moles of ammonia. So, what does this tell us? This tells us if all of the grams of nitrogen given react, we can form 6 moles of ammonia. And if all of the grams of hydrogen given react completely, we can get 8 moles of ammonia. So we compare moles from each conversion. The smaller value will determine the limiting reactant. So this is our smaller value. It determines the limiting reactant. So this is limiting reactant. Okay. Again, I do not label this part. I label the beginning where the reactant is. So if that is limiting, that means that our hydrogen is in excess. So that's the first part. And we labeled those. Now, part 4 says calculate the number of grams of product formed. So remember our question, well, actually it doesn't ask for grams, but it says how many moles of ammonia can be formed from each of these. So this would be our moles of ammonia formed. We would no longer use this number for anything. It doesn't give us anything. What we can do though is if we wanted to find our grams of product, so I want to know how many grams of ammonia is formed, we can just convert this from moles into grams. So I'm just going to add that on so you guys can see that. Moles of ammonia. We want grams of ammonia to figure out how much product did we actually form. 1 mole. And our mass of ammonia. So we've got 14.01 for the mass of nitrogen, plus 3 times our mass of hydrogen, and we get 17.04 grams of ammonia. So now we take that and we're going to multiply by 6. 102.24 is our mass of ammonia that's formed. Ran out of space here. So equals 102.24. We want 4 significant figures, so 102.2 grams of ammonia. And that's how many grams of product we can form from this. So let's talk about this. Our whole process here, the whole point of doing these steps is to figure out which one of these reactants controls the reaction. Once we find our limiting reactant, that's like our given. We ignore the other one. This becomes our given value because it's the one that's going to run out first. You cannot make more product. We can't make these 8 moles of ammonia that we calculated here because we've run out of nitrogen at that point. We can only make 6 moles of ammonia. So that is our process for calculating limiting reactants. There's one more down below, so if you want to pause the video and try that one on your own, and then come back and you can check it with me, you can do that. Alright, so I figure I'm going to run out of space. Let me grab some paper. I can do this one on a separate piece of paper. Alright, so we have in this last example here, so hopefully you've tried it on your own, seeing if you can do it, and now you can check it with me. So you have adipic acid is used to produce nylon, and is made commercially by the reaction between cyclohexane and oxygen. So we've got our reaction there. We've got cyclohexane, C6H12, and we are forming what is it called again? Adipic acid, sorry, and water. So again, we've got our balanced reaction, we've got our coefficients. So you carry out this reaction with 25 grams of cyclohexane and 25 grams of oxygen, equal amounts of reactants. How many grams of adipic acid, so that's what we're looking for, are formed from this reaction? So we have to pick a reactant to start. Well, we have to decide which reactant is limiting so that we can figure this out. All right. So we're going to start out with our cyclohexane there. I'm going to do this on another piece of paper. So we've got 25.0 grams of cyclohexane, so that's the C6H12. Alright, we're going to go from grams of cyclohexane to moles of cyclohexane. We need to find the mass of that. So, we have 6 carbons, so 6 times 12.01, that's mass. I'm going to add to that 12 times 1.01 for hydrogen, 12 hydrogens, 84.14, or 18, 84.18 grams in 1 mole of cyclohexane. So that gets rid of our grams. And remember, we want to get to moles of the product. Now, this is one does have it's slightly different. It's not a synthesis reaction. We have 2 products. So which product are we going to convert to? Now, that's when we want to refer to our question, maybe even look at like a part B of a question or part C to kind of see what is going to be asked later so that we can get to the right product at the beginning. So since our question is going to ask about the adipic acid, not about the water, we're going to convert to the adipic acid. So we're going to go from moles of cyclohexane to moles of the adipic acid. So H2C6H8O4. All right. So we're going to use our mole ratio here. So our cyclohexane has 2 and our adipic acid is 2. So it's 2 to 2 or a 1 to 1 ratio. And we can go ahead and calculate that one. So we've got 25 divided by 84.18. We get 0.2969826, big number. We want 3 significant figures. So 296, the 6 will round up to 7. So 0.297 moles of H2C6H8O4. All right. Now we're going to do the same thing, but with our other reactant. So we have 25 grams of oxygen, O2. Let's just scooch that up for now. We'll come back to it. So grams of oxygen to 1 mole of oxygen. Oxygen has a mass of 16 times 2 would give us 32 grams of oxygen. So again, we want to convert to the moles of the product. So get rid of moles of oxygen. And we want to convert to moles of the adipic acid. We want our units here to match moles of adipic acid on both. We can't compare two different products. It's like apples and oranges. So, look at our balanced reaction. We have 5 moles of oxygen for 2 moles of adipic acid. And we convert. So we have 25 times 2 divided by 5 and divided by 32. 0.3125 is the answer I get. So we want 3 sig figs. So 312, 2 will change to 3. So 0.313 moles of H2, oops, sorry, you guys can see, H2C6H8O4. So now we have our 2 amounts. This is where we want to compare these. We look for the smaller number. It happens to be this one, so 0.297 moles of adipic acid. So we go all the way back to our chemical we started with, and we label that as our limiting reactant. And we check out the other one. This is our one that we have too much of, so oxygen is our excess reactant. So we've discovered the limiting and the excess, but doing all of that, it says in our question, how many grams of adipic acid are formed from this reaction? It didn't say specifically to find the limiting or excess, and they won't always say to find limiting and excess. But to solve this question, you have to do that first, because we need to know which chemical to base our reaction off of. So we're going to base our reaction off of our cyclohexane here. So we want to find the grams of product formed. So instead of starting all the way back at this, we take our moles of product, since I don't have room on my paper, bring that down, so 0.297 moles of, oops, sorry, you can't see it, of the adipic acid, so H2C6H8O4. And we want grams of that. That's what the question asks. So we go from moles of that chemical to grams. Okay, now we're going to add all this up. So, in our calculator, we want 2 hydrogens, so 2 times 1.01 plus 6 carbon, so 6 times 12.01 mass of carbon, plus 8 times our hydrogens, 1.01, plus 4 times our oxygens mass, which is 16. 146.16 grams per mole. So our answer, we're going to multiply 146.16 by 0.297. We get 43.3 sig figs here, so 43.4. You guys can see that, sorry. 43.4 grams of adipic acid, H2C6H8O4. And that is our final answer. So, this process, it is a lot, but it's none of the steps, we've done all these steps before. It's just doing them in certain ways to get some information to help us make some decisions on our problems. So, it just takes some time and thinking through what you're actually doing. Something I can't say enough is make sure when you label your limiting and excess, you're labeling the reactants. I have too often seen people label this piece, and this is a product. So you can't call it a limiting reactant. Something completely different. I hope that helped give you guys some ideas on how this works. Try out your homework.